Okay, so let's continue with our description of the quantum theory of the electromagnetic field. So, if you remember that we had left off at a stage where we had to solve these two coupled equations. So, we had postulated that the Hamiltonian of the electromagnetic field is writable in terms of creation and annihilation operators, which we denoted by small a. So, we denoted it by a subscript j k. So, this k refers to the fact that you are dealing with a continuum, and the j's will actually refer to the two polarization states which are mandatory for transverse electromagnetic field. So, now let me remind you what are the equations that we have to solve, and they are the following. One is the equation which relates the commutator of the commutator of A with P. So, if you remember that the P's and the position coordinate in for the electromagnetic field is just the vector potential, and the conjugate momentum is basically something like a electric field. Okay. So, so what we are supposed to do, well, we are supposed to handle these kinds of equations, and the energy eigenvalue is going to be denoted by capital omega k times aj k commutator am r dash. Okay. And then there is this equation which tells you so there's this Poisson type of equation that we have to solve, and so I am just reminding you where we left off last time, because I had done all this. So, I am just reminding you. So, we are supposed to be solving this, and okay. So, like I have been repeating several times, it is important for you to try this out on your own. Just don't take my word for anything that I say here, just work it out on your own. So, now notice that this equation relates the commutator of A with the vector potential, that is the annihilation operator of the photons, as it were, with the vector potential, and that is what this commutator is, and it relates it to the commutator of the annihilation operator of the photons with the corresponding conjugate momentum. So, we need to know all these quantities explicitly, this, and also this. Remember that we still do not know what, we just know that it is an eigenvalue. So, just like in all other problems in quantum mechanics, the eigenvalue is also to be found by solving the corresponding Schrodinger type of equations. So, here too we will be forced to, we will not know this a priori, we have to find out what it is. So, this is one equation. The other equation relates these two coefficients, namely the commutator of A with the conjugate momentum to the commutator of A with the vector potential. So, they are proportional, and if you combine these two equations, you get a closed Poisson equation, which you can easily then solve. So, the closed Poisson equation is as follows. Well, in this case, well, it is not really Poisson equation, is it? It's more like Helmholtz equation. Okay. If there was some other variable here, like a density, it would be Poisson equation. Actually, it's Helmholtz equation, because this is the same as this. Well, at this stage, you can call it whatever you want, but this is really Helmholtz equation. Okay. So it's going to look like this. So it's easy to now solve this. So I've just combined these two equations and written this equation, and then the easy solution to this is as follows. Times the value of this at r dash equals 0, if you wish. I mean, this is the integration constant. The integration constant, and this is clearly a simple solution of this, and we are going to stick with this solution. And this notice that u cap is an arbitrary unit vector, which we'll have to fix later. So how do you fix that? And so see, in order to fix this, first we notice that this A itself is by definition a linear combination of the the generalized position, which is this, and the generalized momentum, which is that. So just like in the case of a simple harmonic oscillator, if you remember, the annihilation operator was a linear combination of the position and moment, the canonical position and canonical momentum. But in this case, for the electromagnetic field, the canonical position is really the entire field of vector potential, and the canonical momentum is basically something like the electric field. So I'm going to be able to write this in this fashion. So using that idea, I can think of this as something into, it's some linear combination of A's and the P's. So P subscript A implies that the momentum conjugate to A. This M is it carries over from this. The M is corresponding to this M. So now how do you do this? I'm going to convince you that this is correct by evaluating the commutators. Okay, I wrote too many integration signs here. D cubed r prime times ajk commutator am r dash. Okay, so that's the okay, I mean, I'm jumping the gun. I should have written, okay, first let me write this I don't want to swallow too many steps, so I'm going to do it like this. Okay, this makes sense. Okay, this makes sense. This is plus. Okay, this makes sense for what reason? Okay, so the reason why this makes sense is if you take A, J, K commutator, suppose you take PM R dash. So, what is going to happen is that A commutator P is going to be I h bar Dirac delta R. Well, firstly you should convert this to a dummy variable, because see, first of all, A commutator P is only going to contribute because of this term, first term. So, it is not going to be contributing because of the second term, because the second term is already proportional to P and A commutator P is 0. And notice that A commutator vector potential is just a number, and A commutator conjugate to vector potential is also just a number. This is very similar to the simple harmonic oscillator, where the annihilation operator is a linear combination of x and p, and the coefficients are of course constants, and these are those coefficients. Okay, these are those coefficients and they are constant. So, so if I take the commutator of A and the conjugate to vector potential, this is going to drop out, this is going to survive, and you are going to get an I h bar, which is going to cancel out from here, and you are going to get a Dirac delta of R dash dash minus R dash. So, in other words, that is going to force R dash dash to become equal to R dash, and you get back basically you get an identity. So, this is just a it's just a way of representing the knowledge that A is linear in vector potential and its conjugate, and the vector potential and its conjugate obeys canonical commutation rules. Okay, so so once you have understood that, we can use this idea to pin down the quantities we do not know about, namely this the nature of this unit vector u and the energy and so on. So, I am going to substitute these kinds of expressions, and so remember that once I know A commutator P, from this relation I also know A commutator vector potential. So, I know everything as a function of R dash, so long as I fix the other quantities there. So, I am going to use these two and substitute in the expression for A, and I get this result. Okay, so so I apologize for this. I mean, I shouldn't really apologize, because this subject is quite technical and the calculations are quite tedious, and the notation becomes quite clumsy, because of when you are dealing with fields, there are a large number of degrees of freedom, and you have to invent subscripts, superscripts, and arguments and so on. So, very quickly the notation becomes unwieldy, and it is not pretty to look at, no slide is pretty to look at. So, that is the reason why I suggest that you should go ahead and work out all these ideas on your own, so that you become comfortable with what I am saying. So, all right. So, I am going to just substitute the expressions, and they are going to look like this. Four pi c times PAM R dash. So, notice that this is that integration constant there. Okay. What I am going to do is that I am going to first use this to write down the corresponding conjugate with a different polarization index and a different wave vector, and that's going to start to look like this. Can I just take the Hermitian conjugate of this expression, change j to j dash and k to k dash, and I get a new formula for the adjoint of A, and that looks like this. Well, there's this term which says minus IH bar C over omega k dash times 4 pi C okay. So now the idea is that I'm going to enforce or impose canonical commutation rules. I'm going to insist that this commutator is going to be j comma j dash delta of k comma k dash. So now you can see that, look, this is going to be the case only if u has the property that okay, so this is this is times this is an exponent. Okay, so this becomes u dash, okay, because everything becomes dash. So even the unit vectors, because finally they are also getting summed over, so so you'll have to sum over the unit vectors as well. So now if you want this to be the case, then you see the only way this can be accomplished. So if you want to get a Kronecker delta, so basically what you should get is the integral over okay, so let me write it down and I'll argue it out. So I'm going to assert that the u dash unit vector times omega k dash divided by c h bar is equal to k dash vector, okay, and u vector times omega k over c h bar is k vectors. So notice that this is a unit vectors. So if I decide to take the mod on both sides, the mod of unit vector is 1. So that immediately tells me that omega k is basically c h bar times mod k, okay. So that's what it is. So that implies that this unit vector is basically the k hat unit vector, okay. So that immediately follows from this idea, okay. So if I use this idea and I carry out these integrations, so I'm going to skip some steps because it can become quite tedious. So basically the idea is that you have to evaluate these commutators, and the way you do that is you take this expression and take the commutator with that. So a commutator p is some Dirac delta function times a Kronecker delta, and similarly this commutator with a is also like a Dirac delta times a Kronecker delta, and so you will get a whole bunch of Dirac deltas and Kronecker deltas, and So finally, you will be end up with this constraint that the Kronecker delta that survives has to be equal to. So I am skipping a whole bunch of steps because, like I told you, the subject is not very pretty, and it's easier for me to show a typed document. So it's much harder for me to write. So I urge you to fill in the gaps on your own. In any event, even if I flash pre-prepared transparencies, you would still not be able to follow unless you work it out on your own. So basically, the idea is that you will end up with a whole bunch of Dirac deltas and Kronecker deltas, and the constraint that survives is the following, namely this. So the other point I want to make is that this course is not going to this is strictly not part of the syllabus of this course, in the sense that I'm thinking of this as an advanced additional topic for you to learn, but I'm not going to test you in the examination based upon this understanding. So you don't have to necessarily prepare for this subject in order to pass the examination. So you can learn this subject at your leisure whenever you feel like doing so. So right now I'm just giving you some pointers and telling you the direction in which you should move in order for you to understand the subject properly, because this is important, which is why I'm deciding to explain it. But I won't be able to do full justice to the subject because it's not the kind of subject that you can just explain in a classroom very easily. Okay, so that's what it is. So now you can go ahead and make the following. So this can be this constraint can be satisfied by the following assertion. So notice that this M index can be either 1 or 2, because there are two polarization states, and so I'm going to make the following assertions, that A1 commutator PA1 0 is the same as A2 commutator PA20, which is and the other result is A1 commutator PA20 is so if I make these identifications, you can see that this is obeyed. So I go ahead and substitute this here, I get what I am looking for. So this can be compactly written in the following. So these two can be written compactly in the following way. So I'm going to write A1 k vector commutator p vector is square root h bar k over v times 2 pi c times the polarization of this is the unit vector that would correspond to the first polarization direction. So this would be writable. So basically you can always think of this as the, I can always write this in the following way. So basically it's just the linear combination of cos and sine. So it's cos theta k times E1 plus sine theta k. So you just verify this yourself, it's very easy. So where P1 is also by definition, PA vector by definition is PA1 E1 and okay, like that. So now how do you find the EK2? So EK2 is basically given as it's basically the EK1, EK2 and K form a right triad. So you can think of K vector like this, and your EK1 is here and EK2 is there. Okay, so in other words, you can think of EK2 as basically K cross EK1. So that's what it is. So once we know EK1, so you take the cross product of K and EK1, you get EK2. So that will immediately tell you that AK2 commutator PA0 is going to be therefore, so you just work this out on your own. It's going to look like this: h bar k over v times 2 pi c. Okay, so that's what that is. So from here you can easily work out the commutator of the oscillators, or the photon creation and annihilation operators. For example, the photon annihilation operator commuting with the vector potential is going to now look like the following. It's going to have this form, namely it's minus I h r times 4 pi omega k times 4 pi c squared times e raised to I k dot r dash times AJK commutator PA0. Okay, so that's one of the results. The other result is the conjugate to this. You just take the dagger, you get this result. So notice the vector potential is real, so the dagger of that is itself. However, the annihilation operators become their adjoint when you take the conjugate, and I end up with this result. So I'm going to postulate that this is real, because there's no loss of generality, because then the phases can be absorbed by a redefinition of the phases of the creation and annihilation operators. Okay, so this enables me to write, for example, I can invert this. I can think of now the vector potential, therefore, as being related to the oscillators or the creation and annihilation operators of the photons. Okay, so this is actually the ultimate goal. So you must have forgotten by now what it is we are trying to do. So what we are trying to do is basically describe or demonstrate or prove that the electromagnetic field is indeed made of photons. So, the way you do it is to somehow finally convince yourself that, say, the vector potential. So, if you work in the radiation gauge and if it's free space, then the only thing you should worry about is the vector potential, because the magnetic field is the curl of the vector potential and the electric field is the time derivative of the vector potential times minus 1 by c in CGS units. So that's all you have to know, the vector potential. So if you can convince yourself that the vector potential is somehow related to creation and annihilation operators of photons, or basically some kind of oscillators, bosonic oscillators, which you call photons, then you are more or less done, because that's a confirmation that the quantum theory of the electromagnetic field is described in terms of quanta that obey bosonic algebra, or they have bosonic character. All right, so we are nearly there, in other words. So by appropriately combining, so this implies basically that you can express the vector potential in terms of the creation and annihilation operators in the following way, and namely so it's going to look like this. Okay, so now I'm going to substitute these formulas here, and I get this result. Okay, so I'm going to be able to write like this. So this is A r dash, so this is going to look like this. Plus the Hermitian conjugate, because A is real, so it's naturally the whatever comes later is the Hermitian conjugate of this. So now remember that I have written down an explicit formula for AJK commutator PA is 0, and that is this. So if it's J, it's basically this J. So this is what we have explicitly written it down. So I'm going to use that there and complete my calculation, which basically tells me that the vector potential is now expressible in terms of the creation and annihilation operator of photons. Okay, so this is the complete story. So this tells me that this means the quantum EM field is made of photons, and these are those photons. So these are the operators that create and annihilate photons, and that's it. That's pretty neat. And what are the energies? Basically the energies are you see the energy of each photon with momentum k, and polarization J is basically h bar times ck. Yeah, h bar k is the momentum, and momentum times c, which is speed of light, is the energy. So that's my energy of the photon. Okay, so that's the energy of the photon, and the number of quanta would be basically, it's an operator. You see that this would be the number of quanta, or this is the number of photons with momentum k and polarization state J. So now this completes the description of the electromagnetic field in terms of photons. So strictly speaking, this is not part of statistical mechanics per se, but like I told you, it's important to know the finer details or the deep reason for why the electromagnetic field is thought of as photons, because remember that Planck's black body radiation was kind of accounted for by postulating that light is made of the energy content of light is in the form of quanta. So you see, even though Einstein did not know all this quantum theory of the electromagnetic field, which was done of course by Dirac much later, Einstein got it right. I mean, his intuition was fully correct, and that the electromagnetic field should be thought of as carrying energy in packets, in discrete packets. And the deeper reason for why that is valid is because when you start with the electromagnetic field as a classical field, and then you try to apply the rules of quantum mechanics to a classical system the way you normally do in quantum mechanics, you naturally end up with that result which Einstein guessed, namely that the electromagnetic field consists of photons. So now this, you may think of this description what I have given you till now, which is attributable to Dirac, as the rigorous explanation for why the electromagnetic field may be thought of as being made of photons. Okay, I hope you enjoyed this lecture, even though it's not part of the syllabus of this course, but it's kind of one of those appendices which you should know, even though you don't need it to pass an examination. So I'll see you next time with another of these so-called advanced topics, but I'm sure you will enjoy it also, because as you proceed in your education, you will find that most of these topics that I am discussing are actually quite important, and you won't find them all that advanced anymore. Okay, thank you. Let's meet again.